We're going to go through a couple of conceptual questions. These conceptual questions are going to be along the we'll have the concepts of electric flux. So our first question here, what do you think this answer would be? So the correct answer here is A. There's a couple of ways to look at this. One, since flux is the flow of electric field lines and they've given us a picture, we can flat out count the number of lines passing through. So A has 1, 2, 3, 4, 5, 6, 7, 8, 9 lines passing through. 1, 2, 3, 4, 5 lines passing through. The surface area A has more lines passing through it. But again, remember when we draw a picture with electric field lines, how close they are is an indicator of how strong the electric field is. So surface A is closer to that point charge, which means it's in a region where the electric field is stronger. And so with flux being, technically this one would require us to integrate because the electric field would not be uniform. But in general, the electric field, as it passes through A, on average is going to be stronger than the field as it passes through B. So stronger as passes through A. And again, the number of lines are representative of that as well. The reason we would need to integrate is because the electric field up here is different than the electric field here or here. So it has different values at different locations on surface A. Now, we're not going to integrate in this case. I'm not going to ask you to integrate either. We're going to keep it on a simpler scale for our class. But I wanted you to recognize why integration would be necessary if we were to calculate for this electric flux. Okay, I have one more question for you. So the correct answer here is D. So this shape here, A represents the left side. So this back rectangle is A. B represents the slanted side on the front. So this slanted side. And C represents the bottom down here. Our electric field lines are coming in horizontally. If I were to extend these, surface C will have no flux. That bottom surface, none of these electric field lines will pass through the bottom surface. So imagine it's sitting on the floor and these electric field lines are parallel to the floor. None of the field lines are going through that side. Nor are they going through this triangular side we see in the front or in the back. Okay. Now, as we look at this top line is going to come in through A, but then it comes out through surface B. That's going to be true for the second one. It's going to come in to A, out through B. Same with the third one, in and out, in and out. This bottom one is the only one that does not go in or out. Because we have this uniform electric field, all of these lines pass in A, but then as they continue, they also pass out of B. So A and B, both of those surfaces have the same number of field lines passing through. And this is why they have the same magnitude of flux. They have the same amount of field passing through. Now, granted, surface B is most definitely bigger than surface A, but the electric field is horizontal, while the area vector would be normal to the surface. We would need to know this angle between the two of them to calculate the flux mathematically through that surface. It turns out the area of surface B times the cosine of this angle is going to be the same as the surface area of surface A. And that's why if we calculate the electric flux for surface A, the electric field and area vector are already perpendicular, we'll get the same value. So if you have a picture representing electric field lines and some sort of areas that you're looking at the flux through, you can totally count field lines because the field lines are always drawn in a way to be representative of that strength. Now, one side note, because the next topic we're going to get into after the sample problems is flux through a closed surface. This shape, some sort of wedge here, would represent a closed surface. The flux through a closed surface is going to be the sum of the flux through all of the surfaces, all the faces. When it comes to the area vector, surface A's area vector will point to the left, opposite the electric field in this case. Whenever we have a closed surface, the area vector is still normal to the surface, but it specifically points outwards. And that's why surface A, its area vector, I'll put A sub A. This one was A sub B. I already drew that one pointing outwards. So technically, the flux through the left side is going to be negative, while the flux through the right side is positive. What we mean by that is negative flux means the electric field lines are going inside that closed surface. And positive flux, we mean those field lines are coming out. They're pointing outwards. And we'll talk more about that as we talk about closed surfaces in general.